Good morning, I'm Pietro Magarò from University of Calabria and I'm pleased to present you the work entitled Wear Behavior of Cold-Sprayed Stellite-6 Coatings during Reciprocated Dry Sliding. Thermal spray is an industrial method used to improve the surface properties of engineering components in terms of corrosion resistance and especially in terms of wear resistance. In particular, cold gas dynamic spray is a solid-state process that allows to reduce the risk of oxidation phenomena and help to prevent possible residual stresses within the coating. Cold gas dynamic spray is a coating deposition technology in which solid powders with a diameter of around 40–50 microns are accelerated towards a substrate via supersonic gas jet. Due to their high kinetic energy, particles undergo large plastic deformation during the impact with the substrate, and the consequent adiabatic shear instability provides material flow and heat for bonding. And these mechanisms actually represents the main driving force for the adhesion and cohesion of the coating. In fact, the term cold indicates that maximum temperature reached during the process is below the melting point of the material. A high-pressure cold gas dynamic spray equipment produced by Impact Innovation was used for the production of the samples, while a commercial Stellite-6 powder with a particle size of 45 microns was employed as feedstock. The process parameters imposed for the coating deposition are 970 degrees and 4 megapascal for the carrier gas and 300 mm per second for the scanning speed. Standoff distance was set equal to 20 mm. The cross-sections of the obtained Stellite-6 coating are presented in this slide, and how you can see from the higher magnification images, the particle boundaries maintain their round shape, and this result can be related to the resistance to the formation of the Stellite-6 powder. Moreover, the deposition mechanisms involve mechanical deformation of both sprayed particles and steel substrate at the impact surface, as a consequence of the higher Stellite-6 hardness compared to the steel substrate. Moreover, are also shown the detailed characteristics of the dendrite deformation within the particles that are typical for the cobalt-chromium system. The experimental tests were carried out on a reciprocating sliding test rig in dry room condition. It has temperature around 25 degrees and relative humidity around 40%. The wear tests were performed in order to evaluate the influence of the sliding speed and applied load on the wear mechanisms. And in particular, two values of the sliding speed were chosen, it has 0.1 and 0.5 meter per second, and four values of the contact pressure in the range from 2 to 5 megapascal. Sliding distance was kept constant for all experiments and in particular was set equal to 500 meters with a stroke length equal to 26.4 millimeters. The sliding geometry chosen was an iron flat type using cylindrical pins, and each sample was polished using a diamond solution, obtaining a surface finish of 0.2 microns of average roughness. Post-wear characterization consisted of weight measurements for both plate and pin in order to measure the volume loss and the consequent wear coefficient. In this slide, I reported the trends of the dynamic coefficient of friction obtained from reciprocating sliding wear experiments as a function of the sliding distance for the different values of the contact pressure and for the two investigated sliding speed, 0.1 and 0.5 meter per second. And how you can see, a non-uniform peak and valley trend was captured in the case of low speed, in particular for the low values of the contact pressure 2 and 3 megapascal. On the contrary, nearly constant trends were recorded at the higher sliding speed, that is 0.5 meter per second. The average values of the frictional data obtained through the entire sliding distance for the different values of contact pressure and speed analyzed show how the coefficient of friction tends to decrease with increasing the contact pressure for low sliding speed, that is 0.1 meter per second, varying in the range from 0.4 to 0.65, and on the contrary, a slight increase with the contact pressure is observed at higher speed, which is in the range of 0.35 to 0.45. These behaviors are attributed to distinct wear mechanisms, and to this time, systematic analysis of the wear tract were carried out by light micrographic investigations in order to understand the wear mechanisms and with the purpose to capture possible local effects like pull-out phenomena, cracks propagation, and so on. In fact, for the tests carried out at low sliding speed, that's 0.1 meter per second, the wear mechanism seems to be mainly abrasive throughout all experiments, with the evidence of pull-out phenomena on the morphology of the wear surface. In fact, it can be summarized how wear mechanisms seem to be a consequence of the formation of grains on the worn surface as a result of pull-out phenomena observable in all tested samples. Grains, in fact, are typically formed after wear tests for thermal spray coatings and generally are responsible for a type of fatigue wear named grain wear, consisting of pull-outed particles that form small flattened oxidized debris on the wear surface. In addition, the evolution of volume loss and wear coefficient as a function of the contact pressure, shown in this slide, indicates how both volume loss and wear coefficient tend to increase, increasing the contact pressure, as a consequence of the higher density of pull-out phenomena, as confirmed by the microscopic observations. This evidence, in fact, suggests how, in this case, R-shard-like wear models cannot be employed. Regarding tests carried out at 0.5 meter per second, the worn surface is characterized by grooves parallel to the sliding direction and appears affected by pull-out phenomena only when the contact pressure is set equal to 2 MPa. In fact, increasing the contact pressure, the damage mechanisms involved can be mainly attributed to the adhesive wear. So, increasing sliding speed from 0.1 to 0.5 meter per second, a mild to severe wear transition occurs due to the high temperature reached in the contact zone as a consequence of the higher value of the sliding speed. Nevertheless, in these sliding conditions, Stellite-6 coatings exhibit a linear trend of the volume loss, as shown in the present slide, and therefore an almost constant trend for the wear coefficient, that is in accordance with the R-shard equation. The nano-indentation measurements carried out on the cross-section of the samples tested under low sliding speed condition, that is 0.1 meter per second, highlight an almost flat trend for both elastic and hardness responses as a function of the coating depth. However, it's interesting to note that reduced Young modulus is lower in the sample tested at contact pressure of 2 and 3 MPa compared to the case of 4 and 5 MPa, varying from around 218 to 238 GPa. On the contrary, nano-indentation measurements carried out on the coatings tested at 0.5 meter per second show a significant reduction in both elastic modulus and hardness response as a function of the contact pressure. This phenomena can be explained taking into account that the trend observed for stiffness data at low speed can be related to the closure of subsuperficial defects below the worn surface, whereas regarding the experiments carried out in high-speed condition, the observed reduction in the hardness values along the thickness can be related to the ignition of cracks and detachment of materials below the surface occurred during the slide as shown in the images presented in this slide. So the consequent reduction in the elastic modulus is mainly due to the allowed rigid motion of particles debonded from the coatings. In conclusion, detachment and pull-out phenomena mainly affect the worn surface of the coatings tested in low-speed conditions. On the other hand, adhesive wear mechanism is operative for high-speed tests in accordance with the theory of wear for the steel cobalt-chromium system. Plastic deformations, in fact, occurring during the sliding cause the ignition and propagation of cracks within the coating, usually at splat boundaries or in correspondence of pores. So the consequent detachment of material results in wear particles. Regarding the evolution of dynamic coefficient of friction, these latter tend to decrease with the contact pressure because particles can be reintroduced into the wear track as a consequence of pull-out phenomena, and the heating produced during the sliding causes the formation of oxidized pull-out particles that act as solid lubricant. Concluding, cross-sectional material analysis showed a different material response after low and high-speed tests. In fact, at 0.1 meter per second, an increase in stiffness with the applied load was observed as a consequence of the closure of subsuperficial defects below the worn surface. On the other hand, at 0.5 meter per second, a reduction in the stiffness and hardness response as a function of the contact pressure was captured due to the formation of subsuperficial cracks inside the coatings. Thank you for your time and for your attention.